Hello everyone, I hope you're doing well and welcome back to the Math Chaos. For today we have this exercise. Let f from r to the interval between 0 and infinite be differentiable at a in r, and depending on this, evaluate the limit. Here we have the limit when x approaches to 0 of f of a plus x all over f of a rise to the 1 over x. Okay, excellent. Here we can see something. For example, in this first part, when f or f of a plus x over f of a, if we evaluate this and this limit, we can see that it approaches to 1. Why? Because, as you can see, x approaches to 0. A plus 0 is a. F of a over f of a approaches to 1. Okay, excellent, very well. And after that, here we will have that 1 over the x approaches to infinite. Why? Because 1 over values so close to 0 approaches to infinite. Okay, you can do this limit by yourself. Then what happened? It implies we will have 1 to the infinite. And if we have something like this, we can apply ln or natural logarithm. Also, we can see that f of a is well defined because we don't have any determination there. Because f of a couldn't be 0 or can't be 0. Then we will begin. Firstly, we will call s, okay? We will call s, let me delete this part. Okay, excellent. We will call, or we will have this limit, and s is equals to all of this. Okay, excellent. And after that, we will apply natural logarithms in both parts of the quality, having uh, this. ln of s is equals to um, the same thing but with the natural logarithm there. Let me delete this. ln. Okay, why we can put inside natural logarithm? Because as you can see here in this part, it's continuous. Okay, and then this is the reason, or in this interval it's continuous. This is the reason that we can apply there this. Okay, here again we will apply properties. We will apply properties of natural logarithm. Then here we can delete, and then we can delete this exponent and rewrite it over there, 1 over x. Okay, times this. Remember that we can do it because the properties of the logarithms. Okay, excellent, very well. And after that, or let me here, I will divide this page with it. Yeah, okay, excellent. Then here we will write or we will use another property of natural logarithms. It could be ln of s equals to uh, the limit when let me rewrite it better. Okay, ln the limit when x approaches to 0 of, okay, here we will apply this. We will have that 1 over x times ln of f of a plus x minus ln of f of a. Okay, excellent. Here we will have it because we have, here we can do this. I'm so sorry, all this parentheses. We can do this. It's because remember that when we have a fraction inside of a natural logarithm, we can divide it in natural logarithm for the numerator minus natural logarithm of the denominator. Okay, and after that, we can rewrite this with ln of s is equals to the limit when x approaches to 0, when x approaches to 0 of, um, here we have the fraction. Okay, we will multiply this 1 over x, then we will have something like this, ln of f of a plus x minus ln of f of a. Okay, excellent, very well. Okay, then here we have this logarithm. But what happened here? As you can see, this is the more or less the formula of derivatives. Then here we can apply the chain rule. Okay, if you want to, you can do this exercise by yourself, and let me know in the comments if you can do this derivative. But okay, excellent. Then we will have this derivative is going to be equals to ln of s equal to um, f prime evaluated on a over f of a. Okay, excellent. Remember, you can do this derivative, you can do it by chain rule, and you will find the same result. Okay, don't forget to type in the comments, and I will read it. Okay, excellent. Here we need to isolate S. Why? Because S is the same limit. It implies that S is equals to Euler to the f prime of a, yeah, over f of a. And excellent, then we found the result. Then this limit that we were evaluating, here, let me, okay, yeah, here we have it. Then what happened? This limit, when we evaluated, with the conditions we mentioned, we will have that it approaches to Euler to the f prime of a over f of a. Okay, excellent. Then we found the result. And please let me know if you have any question in our comments. I'll be attentive. And I guess no more. Have an excellent day. Bye.